filter from part A. In part A, we found that the resonant frequency to be like 503.3 kilohertz. At this frequency, the output voltage is about 1 volt, matching the input in both magnitude and phase. Part B confirms this, showing that magnitude of 1 at resonance. In part C, we varied the capacitance and saw that increasing it lowers the resonant frequency, proving that they are both inversely proportional. In part E, we swept the parallel resistor. As resistance increases, the output voltage relative to the ground also increases. Part F explains this as higher resistance allows more of the input voltage to appear at the output when frequency equals to the resonant frequency. In part G, placing the resistor in series with the inductor changes things. At high frequencies, the inductor acts like an open circuit, and at low frequencies, the output stays nearly constant.
And here for the second question, we performed DC and small signal analysis for the circuit, and here's our calculated values and from the simulation. Then for part B, there's the simulation we did. For part C, there was a bit of a difference because of the beta, the assumed beta and VBE values. The beta was 160 and the VBE was 0.7. And then as we go like to part D, we applied the ACS signal to the inputs of the active filter, and we got this out of the simulation. And then there was a glitch in the resonance frequency as that was just basically because of the infinite impedance between the capacitor and the inductor causing an open circuit. So the V out was equal VN. And in F, that's the simulation we got. And we got the gain as 33.
In the baseband amplifier, basically what we did here, we had to do a lot of assumptions to get our resistor values, and the assumptions we made were the beta value, which we use 160, and we also assumed IC, and all these assumptions are explained in our calculations. And when we run the simulations, this is what we get for part D. For part E, this is the simulation that we ended up getting. For part 2, which is the output buffer, we also did same assumptions, which are explained in our calculations. And this is the DC analysis. And this is the simulation that we get from our oscilloscope. And this is the AC analysis. And the output buffer simulation is what we get here. And for part C, this is the entire circuit with when it is simulated at AM using our AM modulated signal.
Okay, so for our resistor and capacitor calculations, here's the baseband amplifier. So we assume beta equals 160, IC equals 1.5 milliamps, VC equals 6, and VB equals 0.7. So we got a relationship between R12 and RE, and we know R12 has to be greater than RE for more gain. And also we got this relationship between R11 and R13. And we decided that we want R11 to be smaller because it's the unbypassed capacitor, so we want more collector emitter gain. So then we find R9 and R10, and we want R9 to be greater than R10 so that we limit the amount of current that drains through the bottom resistor. Here are our gain calculations for GM and AVO, so our no load gain. This is the AC analysis. We used the T model, and then we found Rin looking into the base of the circuit, and we found 20K. And we used that in our capacitance calculations here. So we said FC is greater than 30 hertz for AM radio. So we got our capacitor as less than 265 nanofarads. So we decided to pick 100 nanofarads. And then for our bypass capacitor, we picked 10 microfarads using trial and error. So then for the output buffer, we just used the values that we were given for VCE and IC. And we were able to get this relationship between R15 and R16. And we want R15 to be much greater than R16 to once again limit current draining to the bottom resistor. So we picked 680K and 165K.
Okay, looking at our design, here we have the active filter, an antenna which is connected here. Here we have the detection circuit. Here we have the baseband amplifier, and finally this circuit here shows our